don't hesitate to interrupt me at any point and ask me a question. I'll stop. We can park it for a second. All right. Good. Okay, sorry, I didn't even realize it was recording. There we go. Okay, so today we're going to take a look at some practice problems. Again, I posted some lecture videos from a previous semester that covered all of the content in chapter 24, which is the carbohydrates chapter. And the carbohydrates chapter is kind of our introduction to biochemistry. If you notice the last couple of chapters, really in the whole textbook, there's amino acids, which we're going to begin today. There's carbohydrates. There's a chapter on lipids. We don't cover that chapter, but that would also be biochemistry related. And so, yeah, let's get into it here. And I bet you that everybody could have answered the first question without even having read the chapter. It says plants convert carbon dioxide and water into glucose in the presence of sunlight. So what a plant can do is it can take CO2 and H2O, and it puts them together in the presence of sunlight. I'll just put HU, and it can make glucose, which is C6H12O6. You can take the time to balance out the equation if you want. But anyhow, did anybody get this one? What would be the correct answer for this one? A, B, C, D, or E? Yeah, I know you knew that one, right? It's photosynthesis, right? I don't remember everything I did in the third grade, but I do remember that. Learning a little bit about photosynthesis. Okay, so photosynthesis is that process. The next question, number 2, says you've got a monosaccharide that's got 5 carbons and a ketone functional group. This is really important. So when we have a ketone functional group, we call that a ketose. So we call that a ketose. And if we have an aldehyde functional group, we call that an aldose. So we have a ketose. And if it's got 5 carbons, then the prefix that we're going to use for that is going to be pent. And so we put that together and we get a ketopentose is what we would call this, a ketopentose. So again, if your ketone is at the top of your Fisher projection, it's a ketose. And if you have an aldehyde at the top, we call that an aldose. All right, so let's take a look at this question, which is much in the same vein. And it says, which of the following is an aldohexose? So first we're going to start it with the aldo section. So aldose is, ALDO. So aldo, so that means we're dealing with an aldose. And you can see that this compound is an aldose, right? This compound is an aldose, right? Because we have an aldehyde at the top. And this one is an aldose. Now the other ones, this one here, this is a ketose, right? Because we have a ketone at the top, and this one is also a ketose. So the answer can't be D-fructose or D-xylose, xylulose, okay? It has to be either lysose, ribose, or glucose. Pardon me on my pronunciation there. So these are all aldoses, but it says a hexose. So hexose denotes that we have a total of 6 carbons. And if we count on the first one, we have a total of 1, 2, 3, 4, 5 carbons. On the third one, we have 1, 2, 3, 4, 5 carbons. So these two would be aldopentoses. So these are aldopentoses, okay? And the one that's going to be the ketohexose is going to be D-glucose. We have 1, 2, 3, 4, 5, 6 carbons. So D-glucose is going to be the answer. It is an aldohexose. So D-glucose, there you have it. And just remember that when you're looking at a Fisher projection, and we covered this way back in chapter 5 of Organic 1, that any place that 2 carbons cross like this, that means we have a carbon, right? There's also a carbon here. But we don't draw those carbons in explicitly in a Fisher projection. All right, and if you need to review that, you could go back to chapter 2 where we look at molecular representations, or chapter 5 where we cover stereochemistry, which is also revisited in this chapter, isn't it? So let's take a look at question number 4. Which of the following best describes the relationship between D-glucose and D-fructose? Well, first of all, if you go over to the handout that I gave you, if we look at D-glucose, so I have it here, and you can see that D-glucose is an aldohexose. We covered that already today, aldohexose. And then if I scroll down to the second page here, you can see that we have D-fructose, and D-fructose is an aldoketose. A ketohexose. Mr. Dion needs another cup of coffee. Ketohexose, like that, because it has a total of 1, 2, 3, 4, 5, 6 carbons, and it has a carbonyl from a ketone, so it's a ketohexose. And so the two compounds, one's a ketose, one's an aldose, but they both have the same molecular formula, right? They are both hexoses, and so they both have the same molecular formula. And so when we go back here, we can say both are C6H12O6, but they have different structures, and so they are constitutional isomers, right? Compounds with the same molecular formula, but a different connectivity of the atoms. Give me a thumbs up if you're with me on the first 4 problems. Everybody with me so far? All right, awesome. Let's keep cooking with gas then. Number 5, which of the following compounds are a pair of enantiomers? So we know that enantiomers are superimposable mirror images. All right. So if we look at all of these compounds, we want to find 2 compounds where every stereocenter is reversed. So these are all aldohexoses, and you can see that every carbon here is a stereocenter. So if we look for 2 compounds that are non-superimposable mirror images, hopefully you could see it would be this aldohexose and this aldohexose here. If you look at the first stereocenter, you can see the hydroxyl is on the opposite side. If you look at this one, you can see it's on the opposite side. This one, it's on the opposite side, and this one, it's on the opposite side. So the answer is 2 and 4 are the 2 compounds that are enantiomers. Are enantiomers of each other. And don't get hung up on any of the other carbons in there, right? Because if you look at this carbon, the one that has the carbonyl, right, that's not a stereocenter. And then this carbon, that is also not a stereocenter because it has 2 hydrogens attached to it. All right, so it's only the 4 carbons that are crossed there where we can't see the carbons. Those are the stereocenters. All right, number 6. It says, of the possible stereoisomers of fructose, how many are D isomers? So let's take a look here. And if we go over to the family of aldoses and ketoses, we'll find fructose again. So here's D-fructose. So let me just delete some of my spinach that I put here. All right, and so what we're going to do is we're going to count the number of chiral centers that we have in the molecule. And if we look very carefully, you see that we have 1, 2, 3 chiral centers in the molecule. So now that we know we have 3 chiral centers, we can go back and solve the problem. So let me go over here, back to the question at hand. All right, so if we go back to that problem, we know that fructose has 3 stereocenters. So 3 stereocenters. And so the total possible number of stereoisomers that you can have is 2 to the power of n, where n is equal to the number of stereocenters. Right? So then if we take 2 to the power of 3, that gives us 8. But remember, it's asking of the possible stereoisomers for fructose, how many are D isomers? So remember that when we're dealing with a sugar, we can have the D isomers, which are the naturally occurring isomers, or the L isomers. That means that half of them are going to be D and half of them are going to be L. So now we have to divide this in half to give us a total of 4 stereoisomers, including fructose. So you want to remember that when we're dealing with any sugars, you look at the number of total stereocenters, you can take 2 to the power of that number, and that gives you the total number of stereoisomers, but only half of them will be D sugars, so only half of them are naturally occurring. The other ones, the L sugars, are going to be unnatural. And something that you're going to see when we get into the next chapter, chapter 25, when we're dealing with amino acids, the L amino acids are the natural ones, and the D are the unnatural ones. Kind of annoying, but that's just the way that nature made it, all right? Anyhow, which one of the following is the correct stereochemical configuration for D-mannose? So this compound here, this is D-mannose, so D-mannose. And if you watch the videos about this chapter, you know that there's a very quick and easy way to determine the relative stereochemistry at each chiral center in this molecule. So we have 4 chiral centers at carbons 2, 3, 4, and 5. Now you could do the long way and say, well, this is going to be my highest priority, this is second, this is third, this is fourth, so I go 1, 2, 3. So that's clockwise, which is R, but this hydrogen is coming out, so I reverse it, and that one is S. So you would say that this compound is 2S, okay? And you would start with that. But remember that the short way of doing it is any hydroxyl that's on the left-hand side of the molecule has an S stereochemistry, and any chiral center that has the hydroxyl on the right-hand side has R stereochemistry. So this compound is 2S, 3S, 4R, 5R, and so the answer is A. Now, if you're wondering why didn't you teach me that way back in chapter 5 of Organic Chemistry 1, now what kind of fun would that have been? It wouldn't have been any fun. No, the reason why we don't cover this in chapter 5 is because we want to get students to avoid trying to find any kind of shortcuts when they're learning the subject, right? And we just want to teach them how to do it the long way, if you will, following the Kahn-Ingold pre-log rules. Anyhow, now you're let in on the big secret, okay? So anything on the left-hand side is S, sinister, right? Anything on the right-hand side, rectus, is right. There you go. All right, which of the following structures represent beta-D-glucopyranose? Okay, so the first thing that we're going to do here is we're going to take a look at a chair. And if I just draw a chair like this, okay, I just want to remind you of a couple things. So this is my best chair. I got going here. So anyhow, there's a chair. So remember that this carbon, okay, this is what we call the anomeric carbon. Anomeric carbon. And if you have something pointing up, we call that the beta position. So up is beta, and down is what we call alpha. If you have something pointing down like this, that's the alpha position. If you have something pointing up, that's the beta position. Of course, beta is equatorial and alpha is axial. All right, so now that we've covered that, if we look at all of these compounds, you see that in the first one, we have the hydroxyl pointing up, so that's beta. This one's beta. This cannot be the answer because the hydroxyl on the anomeric carbon is pointing down, so this is alpha. So that can't be the answer. And on this one, the hydroxyl is pointing up. So now we have to look at the other chiral centers in the molecule and figure out, okay, well, which one is the right compound? Okay, so let me walk you through this if you didn't follow it on my lecture videos. I'm going to show it to you again. And what we're going to do is we're going to start by drawing the structure of D-glucose. So let's draw the structure of D-glucose. I'm going to try to draw it somewhat neatly. Okay, so we have something that looks like this. You'll see that I usually draw my glucose the same way, just kind of the way I cut my teeth on it. Okay, so this is D-glucose. Okay, so when you're drawing a chair, here's what we're going to do. We're going to draw the chair. We'll draw the conformation of our chair like this. All right, excuse me, something like that. And remember, anything that's pointing on the right-hand side is going to be pointing down. So if we have carbon 1, 2, 3, 4, 5, 6, we number here 1, 2, 3, 4, 5. And if you're wondering where's carbon 6, well, it's this one, right, which never changes. So we know that this compound is beta, so that means the hydroxyl on the anomeric carbon is going to be pointing up. It's up and axial, or sorry, up and equatorial rather. That was a mistake. So now all we need to do is figure out carbons 2, 3, and 4. So I'm going to box them in here. Carbons 2, 3, and 4, like this. And anything that is on the right-hand side, okay, so anything on the right-hand side, let me make this a little neater. Okay, right-hand side means it's going to be pointing down. Now, it doesn't tell you if it's down in axial or down in equatorial. You have to figure that out on your own. But if we look at carbon 2, we have the hydroxyl pointing down, so the position is going to be down and equatorial. If we look at carbon 3, the hydroxyl is going up, so it's going to be up and equatorial. And if we look at carbon 4, the hydroxyl is going down, so it's going to be down and equatorial like this. And so whatever compound has the exact same conformation as this, that is going to be our beta-D-glucopyranose. And so if we look at all of these, if you look at the second one, so if we zoom in here, you can see you've got the hydroxyl going down, going up, going down. The only thing they changed is that they rotated this carbon-carbon bond, and there's nothing wrong with that whatsoever. I can do that for you too if you want. We can just put this bond going straight up like this. And there you go. Now we have beta D glucose, or you can call it glucopyranose. It means the exact same thing. Okay. So again, the difference between beta glucose, or sorry, excuse me, D glucose shown over here is that the anomeric carbon doesn't have a chiral center at it. So we can't call this alpha or beta because it hasn't cyclized yet. But when we draw the chair, we can draw it as alpha or beta. And in this case, the hydroxyl is going up, and therefore it's beta. Give me a thumbs up if you're with me on that. Going from the Fisher projection to the chair. All right. And of course, you have to go to the Hayworth projection too, or the Haworth projection, and we'll get some practice on that as well. All right, let's go on here. Number 9. Which of the following compounds is an epimer of D-glucose? So if you remember, epimer is a new type of stereoisomer. So we'll put here epimer, stereoisomer that differs at 1 chiral center. So only 1 chiral center difference, and it's a type of diastereomer, but we call it an epimer. So let's redraw our glucose, or could I just copy and paste it? No, it's too messy. So let's redraw glucose. So maybe I could kind of draw it the way that they have it done here, like this. So I'll try to draw it as neatly as I can. Believe it or not, that's me trying to be neat. So we have 1, 2, 3, 4. So for glucose, we have, oops, 1, 2, there we go. So now we fill in everything else. And so this is D-glucose. So now we're looking for something here that differs at only 1 chiral center. Does anybody see some compounds here that differ at only 1 chiral center? Could anybody identify one? One, two, three, or 4. Yeah, number 1 for sure. Thanks, Avicii. Absolutely. Number 1, can't argue with that. What else? There's another one. Yeah, thanks, Avicii. Good. It's number 1 and number 3, isn't it? Right. So number 1, the difference is at carbon number 2. No, it's at carbon number 1. Sorry, my mistake. And on the third one, it's at carbon number 1, 2, 4. There we go. All right. So the answer is 1 and 3 are epimers of D-glucose. Remember, it's a type of diastereomer, just differs in the configuration at 1 chiral center. All right. There aren't a lot of mechanisms in this chapter whatsoever, but I think this is one where we could draw a little mechanism and it might help us, okay? It says predict the major product for the following reaction. And if you remember, when we studied acetals and hemiacetals way back in, I think, chapter 12, I said, well, hemiacetals, we don't get those very much unless we can form a cyclic hemiacetal. And so you see that there are 2 compounds here in the answers that are hemiacetals. It says predict the major product for the following reaction. And we know from previous experience that if you take an alcohol with an aldehyde, right, you can form a hemiacetal. Well, this one is just an intramolecular formation of a hemiacetal because you have the hydroxyl and the aldehyde in the same molecule, right? So the first thing that we're going to do is we're going to take this compound and we're going to protonate it. So I'm just going to skip drawing the mechanism of that first step, and I'll just draw the oxonium like this, okay? And if you want to, I could maybe draw the mechanism up here. So you take a hydronium ion like that, and you just take a proton. So there we go. Take a proton, just like you would take a centerpiece from a table at a wedding or something, okay? So there's your oxonium ion, and now you know that carbonyl is extremely electrophilic, and you have a decent nucleophile here in the hydroxyl. So you're going to form a cyclic compound here. So let's count the number of carbons in the ring, and of course this is in equilibrium, but anyhow, it's neither here nor there really. If you count, we have 1, 2, 3, 4, 5, 6. So we have 6 atoms in the ring, and one of them is an oxygen. So if we draw something that looks like this, okay, and this is our only 6-membered ring with, no, sorry, we have one here too. But anyhow, maybe I'll draw it the way they have it, okay? So let me fix it and I'll draw it the way they have it in the answer bank. Here we go. Something like this. So if we count, let's say we count from here. We'll put this as carbon is blue. 1, 1, 2, 3, 4, 5, And then this oxygen would be atom number 6. So over here on this carbon on number 1, we're going to have a hydroxyl group now. Here we're still going to have the proton like this, so it's going to be positively charged. And then we've got our methyl group at carbon number 3, so I'll scribble that in. And so the next step is going to be restoring neutrality to the molecule. So you're going to have water acting as a base, right, like this, and the water is going to pull off this proton, and we're going to end up getting this hemiacetal, right? So we end up with this hemiacetal, which happens to be compound number 1, and so the answer is 1. All right, remember that whenever we can form a 6-membered ring, we will do that, right? The formation of a 6-membered ring is always preferred, and so we form a 6-membered ring in this case, and we end up, again, just to review, this is a hemiacetal, right? This carbon has a hydroxyl and an ether attached to it, which means it's a hemiacetal. All right, cyclic hemiacetal, there we go. Which is the correct Haworth projection for beta D allopyranose? So what we need is we need to have allose. We need to have the structure of allose. So without me going back to the handout that you're going to have on your exam anyway, or your quiz, allose is one of the easier, and I don't like to use the word easy in organic chemistry, but it's one of the easier sugars to remember, because all it is this compound, and you have every hydroxyl on the right-hand side like this. So that means that every chiral center is going to have the hydroxyl pointing down, except for the anomeric carbon, right? OH is going to be pointing up. And so all we have to do is draw a Haworth projection. So remember, this is the way we do it. We put the oxygen in the top right corner like this. We draw our 6-membered ring like so, and you can shade in these carbon-carbon bonds if you want, like that. Then we have our CH2OH up here. So now at carbon number 1, that's the anomeric carbon. So the hydroxyl is going to be pointing up because it's beta. And on every other carbon, so if I number them, carbon 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6. All right. Everything that's pointing down, so on carbon 3, 4, and 5, or sorry, 2, 3, and 4, these hydroxyls are all on the right-hand side, and so these are all pointing down. Down. Okay. All right. So we have a hydroxyl that's pointing down here. We have a hydroxyl pointing down here. And we have a hydroxyl pointing down here. So which one of these is the correct answer? It's going to be 3. Everything is pointing down except for the anomeric carbon, which is beta. And so the answer is 3. All righty, let's move on from there. Next question is, which of the following compounds is considered a glycoside? And so a glycoside exists when we have an acetal at the anomeric carbon. So acetal at anomeric carbon. And so you can see that this is a hemiacetal. Here you've got a hydroxyl and an ether. So it can't be this one. Here you've got a hydroxyl and an ether. So this is a hemiacetal. But if you look at 3 and 4, you see that this carbon has an ether on it here, and this one has an ether on it here. And then if you look at this one, we have an ether here, and we have an ether over here. So the answer is 3 and 4. Those are both glycosides. The other two, so we'll put here 1 and 2, these are hemiacetals. Okay, and when we have an acetal at the anomeric carbon, we call that a glycoside. All right, number 13, we start some reactions here. So this one says we're going to reduce D-galactose. So if I draw the structure of D-galactose here, and D-galactose is closely related to glucose. So let me just pencil it in here kind of quickly. So D-galactose looks something like this. So we have a hydroxyl here and here. Yeah, proton, hydroxyl, hydroxyl. There we go. So this is D-galactose. And remember that when we treat an aldose with sodium borohydride and water, what that does is it reduces the aldehyde to an alcohol. So you can answer this one pretty quickly, right? Because here you see this is not an alcohol. This is a carboxylic acid. That's just plain wrong. And so is this. So the answer has to be number 3. All right, so the answer has to be number 3 because we just reduced the aldehyde down to an alcohol. So here it's an aldehyde, right? And here it is an alcohol. Okay, and remember we have a name for this. We call this an alditol. So when you reduce an aldose to an alcohol, we call that an alditol. Alditol. All right, so that covers that one. So the answer for this one is number 3. All right, number 14, another reaction here. It says, which of the following d-aldoses will produce an optically inactive product when treated with sodium borohydride and water? So remember, something that is optically active is something that will not rotate plain polarized light. So does that mean it won't have a chiral center? No, it just means that overall the compound won't be chiral when we reduce it. So could anybody identify that compound here? It's not a trick question. Could anybody identify the compound here that when you reduce it with sodium borohydride, you end up with something that has no chirality? There's chiral centers in the molecule, but it has no chirality overall. All right, so what if we take a look at compound number 3? Okay, if we take compound number 3 and we treat this with sodium borohydride in water, what you're going to end up with is this. You're going to reduce the aldehyde to an alcohol. You've got another alcohol on the end, like this. And then you do have 1, 2, 3, 4 chiral centers. So we have a hydroxyl here, 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 and here. So there are 4 chiral centers in the molecule. However, there's also a plane of symmetry down the molecule like this. What do we call a compound when, even though it's got an even number of chiral centers, there's a plane of symmetry in it? What do we call a compound like this? Anybody? It's got a tsatzy name, starts with the letter M. Nobody? Yeah, exactly. It's a meso compound. Perfect. Yeah, so this is a meso compound. And remember that meso compounds, yes, they do have chiral centers, but they're optically inactive, which means they won't rotate plane polarized light in the positive or negative direction. And so the answer is number 3. Number 3, once you reduce it, you end up with an alditol, again, but this happens to be a mesoalditol. And a meso compound is a compound that has 2 or more chiral centers. This one has 4, but it won't rotate plane polarized light. All right, number 15. Which of the following compounds is a non-reducing sugar? So remember that any sugar that has a hemiacetal at the anomeric carbon is considered to be a reducing sugar. But when we have a non-reducing sugar, so I'll put here non-reducing sugars, that means it's going to be something that's a glycoside. Glycoside. And if you don't remember what a glycoside is, it's something that is an acetal at anomeric carbon. So if we look at these 4 compounds here we have a hemiacetal, here we have a hemiacetal. This one also has a hemiacetal. But if we look at this compound, we have an ether here, and we have another ether here. And so this compound is a glycoside, therefore it's going to be a non-reducing sugar. All right, so non-reducing simply means that it can't reduce copper 2 to copper 1 in the Benedict's test, for example. And I cover that in the lecture video, so I won't go into any more detail than that. The next one says predict the products for the following reaction. So this one we're going to take D-xylose and we're going to treat it with bromine and water. And if you remember in my notes in the textbook, it says this has to be done at a pH of about 6 in order to get this to work. And this is the synthesis of an aldonic acid. So what we're going to do is we're going to take our aldopentose, which is D-xylose. So let me just draw the structure of D-xylose. Just bear with me here for a sec. So if we draw D-xylose, which is this compound, so this is D-xylose, okay? Now, what we're going to do is we're going to oxidize the aldehyde to a carboxylic acid. So again, this is bromine in water, and it's buffered to a pH equal to 6. And so we oxidize that top carbon. So I'm just going to copy this, and I'll paste it over here. And all we do is we oxidize that top carbon from an aldehyde to a carboxylic acid. So we get a carboxylic acid. And remember, when we just oxidize the top carbon, we call that an aldonic acid. So we call this an aldonic acid. Now, if you're wondering what happens when you oxidize this group, you get an alderic acid, and we'll talk about that as well. Hey, what do you know? It's in the next problem. All right, so predict the products for the following reaction. So this one, we're going to take the compound, treat it with nitric acid and water. So it's D-galactose that we're starting with, so we could practice our drawing of D-galactose, which is this compound. We drew it earlier today. So we have this, so 1, 2, 3. So D-galactose looks something like this, if my memory serves me correctly. So there we go. Okay, so this is D-galactose. Right, D-galactose only differs from glucose in this chiral center, okay? So in the third chiral center or the fourth carbon. Anyhow, so if we treat that with nitric acid, what that's going to do is it's going to oxidize both ends of the molecule. So you're going to oxidize the aldehyde to a carboxylic acid and the alcohol to a carboxylic acid. That gives us an alderic acid. So let's take a look here. And if we look at these, well, the one that seems to be right is number 1. Okay, this happens to be the alderic acid we are looking for. We have 2 carboxyl groups on each end, and the hydroxyls are all good. You probably also noticed that this is a meso compound. You can see there's a plane of symmetry here, but that's neither here nor there. So the answer is going to be number 1. Give me a thumbs up if you're with me on the last few problems. Everybody with me? That doesn't mean placate me. It just, if you have a question, don't hesitate to ask. All right, good enough. Okay, next one deals with the Kiliani-Fisher synthesis. So this is a synthesis covered towards the end of the chapter, and it's just a way to elongate an aldose. So it says here, which aldose would produce D-ribose and D-arabinose when subjected to the Kiliani-Fisher synthesis. So let's go and let's look up the structure of D-ribose and D-arabinose. So I've got them here on my handout. So I'm just gonna skip part of it here, and I'm gonna write out the structure of D-ribose and D-arabinose. So just bear with me here. Give it the old college try. So start with D-ribose. So D-ribose has all of its hydroxyls over here. So this is D-ribose. And D-arabinose only differs at 1 chiral center. So I'm just going to copy and paste this. All right, so this is D-arabinose. Actually, it isn't. Yeah, it is it. I have to change 1 chiral center, and that's the one at the top. So I'm going to put a proton here and a hydroxyl over there. Okay, so Kiliani-Fisher synthesis. Remember, this is going to adds 1 carbon. So if we're adding a carbon, all we're going to have to do is chop a carbon off. So we're going to chop off this carbon here off the top. So we're losing that one. And then the carbon that I have in blue, that's the one that's going to become the aldehyde. So if we draw the compound that this is going to come from, it's only going to have 2 chiral centers. Both hydroxyls are going to be on the right-hand side. And you've got your aldehyde up here. And of course, you haven't changed this center whatsoever. And so if you go over to the handout, you'll see that this is D-erythrose. Erythrose is the starting material. That one of the answers? Yep, it is. It's C, D-erythrose. There we go. All right, everybody with me on that one? So the conditions for the Kiliani-Fisher synthesis is kind of a lengthy synthesis. So the first step involves the formation of a cyanohydrin. So that's using HCN, everybody's best friend. That's a joke. Okay, and then in the second step, you have this whole concoction here of hydrogen gas and palladium on barium sulfate. So this is a type of poison catalyst. And then you put it in water. So what the hydrogenation condition does is it takes the cyanohydrin. So we could just put here cyanohydrin is what's formed in this step. And then in the next part, this one here, the hydrogen gas, is going to form the imine, forms imine, and then the water hydrolyzes it. And again, there's no mechanism for this. And the text hydrolyzes, okay? Hydrolyzes the imine, okay? No mechanism for that whatsoever in the textbook, so don't stress about that. All right, number 19. Okay, Killiani-Fisher synthesis again. Predict the products for the Killiani-Fisher synthesis. So again, Killiani-Fisher, we're adding a carbon. So we're starting it with D-ribose. So let's go back here. And we'll just copy the old D-ribose. There we go. Just copy that. And we'll paste it down here. All right, so there's our D-ribose. Let me just get rid of this extra spinach here. Okay, so D-ribose, and then we're going to add a carbon to it. And so when we add a carbon to it, okay, we're going to add a carbon on top. I'll just kind of put a carbon, right? We're going to add something like this. And then this carbon is going to become a new chiral center, but you're going to get a mixture of R and S. Okay, so you'll get R and S. Oops. You're going to get R plus S at this chiral center. So it can't be this one. It can't be this one. It can't be this one. But if you look at 1 and 5, well, those are both possible because you see that you have the bottom 3 hydroxyls all on the right-hand side. You have the hydroxyl here on the right hand, here on the left hand. And so the answer has to be 1. It's going to be 1. And then 5 is the other one. All right, so 1 and 5, is that an answer? It happens to be. What do you know? It's the first answer. All right, there we go. Let's move on. Number 20, practically over. I predict the products of the following vol degradation. Okay, it's a good German name, the vol degradation. So vol degradation means we're going to end up removing a carbon. So you can see that these are all aldopentoses. So we're going to remove the top carbon of any one of these, right? Or sorry, we're starting it with D-galactose. My mistake. I'm getting too far ahead of myself, so that's what I get for doing that. Let's go back and find out where I was. Okay, so let's write down D-galactose. By now you probably have it committed to memory, so we're starting out with D-galactose, which looks something like this. So we have 1, 2, 3, 4 chiral centers. You can see why I didn't become a carbohydrate chemist. It can get tedious drawing all these. Anyhow, so there we go. This is D-galactose, so D-galactose. And so what we're going to do is we're going to remove, sorry, this is where my mistake was. We're going to remove this carbon. And then this carbon here that I'm going to highlight in blue, that's going to become the aldehyde. And so we have to look for something that has 2 hydroxyls here and then a hydrogen here. So that looks right. And so the answer has to be IV, or number 4, okay? So there you go. That would be the product of the vol degradation. Is number IV or 4. Everybody with me on that one? Yes, thumbs up on that one. Everybody? Okay, cool. Just making sure. We only have a few left. So the last page has got some real doozies on it. There's actually one question I went over this afternoon and didn't like it. But I don't have any qualms with question number 21. It just says, which one of these is a reducing sugar? So if we have a reducing sugar, that means it has to have an acetal in it. So we need to have an acetal, which means or not a glycoside, which is, sorry, did I say acetal? I meant hemiacetal. So what we're looking for is a hemiacetal, something that is not a glycoside. So hemiacetal. All right, if we look at the first one, you can see that this carbon has a hydroxyl and an ether. So that's a hemiacetal, so it can't be number 1. If we go over to number 2, you can see that this carbon has an ether and then it has another ether over there. So this is going to be, oh, sorry, we're looking for a reducing sugar, damn it. So number 1 is a reducing sugar because it has a hemiacetal, okay? Number 2 is not a reducing sugar because it is a glycoside. If we look at number 3, well, that's sucrose. So sucrose is not a reducing sugar. I could just tell the structure just by looking at it, but there's no hemiacetal in there. And let's see, the last one here, is that a reducing sugar? No, because there's no acetal in there. There's no hemiacetal in there. No, there's no hemiacetal in either of these. Okay, so the only one that has a hemiacetal in it is the first one. So the answer for this one has to be number one. Sorry it took me so long to go through all those, but I was just kind of looking at them through my glasses. So which of the following disaccharides are alpha glucosides? So I'm going to scratch this one. I'm not a big fan of this question, so I'm going to skip this one for now. I don't like the way it's presented, so I'm going to skip that one. I don't think it's all that pertinent anyway. Number 23 says, which of the following monosaccharides are produced when starch is completely hydrolyzed? So you should know what starch is made of. It's one of the most abundant polymers on the planet Earth, and it's made from alpha-D-glucose. Okay, so starch is made of glucose units that are alpha linked. If you have a polymer made of beta-D-glucose, that's cellulose. Okay, just remember that. Starch is alpha-D-glucose, and cellulose is beta-D-glucose. All right, for 24 and 25, I'm going to switch over to a blank document for both of these. And I'm not going to come back to this page. I'll just read off the questions. But let's read the first one together. Number 24 says, draw the Haworth projection and a chair projection of alpha-D-gulose. So we're going to start out with the Fisher projection of D-gulose, and then we're going to draw a Haworth projection, and then we're going to draw a chair. So just bear with me as I switch over to a blank document here. So let's see. There we go. All right. You can see I was doing some alkynes work with Organic Chemistry 1 earlier. So this is question 24. And we're going to start out with we're going to start out with D-gulose. So if I go over here, I want to make sure I wrote the structure down here. I don't think I made a mistake. But anyhow, so if we draw D-gulose looks like this. So 1, 2, 3, 4 chiral centers in our D-gulose. So we have a hydroxyl here, here, and here. There we go. So now we can just fill the whole thing out like this. So this is D-gulose. Old habits die hard. D-gulose. There we go. Okay, so we're going to start by drawing the Haworth projection. And the way that we do that, this is not a reaction, so I'm just going to put just an arrow like this, right? I guess you could put an arrow to it because technically it is a cyclization, so I digress. Maybe I'll just draw an arrow like this. Okay, if we draw the Haworth projection, we always do the same thing. We're always going to start with our 6-membered ring, and we put the oxygen in the top right corner like this. So then we draw our 6-membered ring, and we can shade in these bonds, and that's optional. You don't have to do that. I'm just doing it because I'm your instructor and I'm probably supposed to. Now we can number the carbons. So we have carbon 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4, 5. And carbon 6 is going to be going straight up. And you can just do this if you want and put an OH group on the end, or you could just say CH2OH like that. Either one is fine. So it's asking us to draw alpha-D-gulose. So we're asked to draw alpha-D-gulose. So that means on our anomeric carbon, our hydroxyl has to be pointing down because it's alpha. So now we need to figure out the chirality at carbons 2, 3, and 4. And at carbons 2, 3, and 4, anything that's inside this blue box is going to be pointing down. So that means that our hydroxyl on carbon number 2 is going to be pointing down. Our hydroxyl on carbon number 3 is going to be pointing down. And our hydroxyl on carbon number 4 is going to be going straight up like this. Okay? So now if we want to draw a chair, what we're going to do is this, is we're going to draw our chair the best we can. Okay, so if we start with numbering our carbons, so I could put this over here like this. So we have 1, let me use my red pen, 1, 2, 3, 4, 5, 6, something like that. So if we go to the anomeric carbon, it's going to be pointing down like this. On carbon 2, our hydroxyl is pointing down, but it's equatorial. On carbon 3, the hydroxyl is pointing down and it's down and axial. And on carbon number 4, it's going straight up and it's going to be up and axial like this. And so this is also alpha D glucose is just the chair. Everybody give me a thumbs up if you're with me on that. Any questions about that? Drawing a chair. We always draw them the same way. And remember, on your quiz or anything that you do that's practice in this class, if you're ever asked to draw a sugar, it's going to be a naturally occurring sugar. So it's going to be a D sugar. Okay, you're not going to be asked to draw any L sugars. So I'm going to go down to question number 25. I'll just read it aloud here. Question 25 says, draw a chair conformation of the disaccharide formed between two molecules of D-allose, so D-allose, and they're linked by an alpha linked, no, sorry, by a 1,4 beta D, so 1,4 beta D glycosidic bond. Glycosidic linkage is what they're asking us for. So the first thing I'm going to do is, and again, it's asking us for a chair, is I'm going to draw a molecule of D-allose. So let's start with that. D-allose looks a little something like this. We drew this one today as well. And again, I said it's not that difficult to memorize D-allose because all the hydroxyls are pointing to the right-hand side, right? Like this. Pass the allose on the right-hand side. Okay, so first we're going to draw a chair. And I'm not going to go through the whole dog and pony show about how to do that. So I'm just going to draw one chair. That's not a very pretty bond. That's a little better. No, that's ugly. Well, let's fix this thing up here. Mr. Dion, I think you need more coffee. All right, so there you go. All right, so it's linked by a beta D-glycosidic linkage. So our hydroxyl and the anomeric carbon is going to be going up like this. Then at carbons, oops, put in this carbon here. At carbons 2, 3, and 4, okay, all the hydroxyls are pointing down. So this one's going to be down and equatorial. This one's down and axial. And this one's down and equatorial. Like that. Okay, so there's our molecule of beta D-allose. So this is beta D-allose. So now what we need to do is we need to link two of these guys up together. So I'm going to do some copying and pasting here just to save a little time. What we're going to do is we're going to copy this guy. So we'll put him here. Okay. And then we're going to paste another one here. And what we need to do is we need to link these two together. And you can see that the bond here, if they want us to do a beta 1,4 linkage, right? That's what we're seeing here. Beta, oops. It's beta 1 and 4. I didn't mean to color code that there. But what the beta means is that this bond here is beta, right? That it's going up in the glycosidic linkage. So we're going to take that hemiacetal and we're going to convert it to an acetal. So to do that, we're going to erase this, this, and this, okay? And now we're going to link these two guys together like this. And of course, you lose water at the same time. So maybe I could do that a little bit better like that. So this is our beta, and this is carbon 1. This is carbon 4. So that's where you get beta 1, 4 is how you label that. All right. So there you go. So, and we're also beta, it's shown as beta over here. But that is how you would put those two sugars together to get a beta 1,4 linkage for your disaccharide. All right. And again, this is kind of an introduction to biochemistry because in biochemistry, you're going to talk about sugars a lot. You're going to talk about the Krebs cycle, the citric acid cycle, the electron transport chain. And of course, the sugar that you're going to deal with mostly is glucose, of course, in that class, but you're going to see some others along the way. And so, yeah, it's kind of an initiation into some sugar chemistry.